So welcome to today's physics colloquium, which will be given by David DiVincenzo from Aachen and Jülich in Germany. And David really is a pioneer in the implementation of quantum computing, and he's well known mostly for two pieces of work. One is to set up a set of criteria that every implementation of quantum computing has to satisfy, a set of 5 criteria, I believe. And the second is a joint work with Daniel Loss from Basel, where they propose to how to implement quantum computing with quantum dots. Let me say a few words about David's career. So he did his PhD in 1983. In electrical engineering, actually, in the University of Pennsylvania. Then afterwards, he did a postdoc at Cornell. And from 1985, he joined IBM as a research staff member and stayed there until 2011. This is the reason we invite David here. We want to welcome him on the continent, because in 2011, he took up the position as a director of a theoretical nanoscience center at the Forschungszentrum in Jülich, and also as a professor on theoretical physics, I guess, at the University of, or at the RWTH in Aachen. And so David has received many honors. In particular, he's a fellow of the American Physical Society. And with that, I'd like to welcome him. To give this talk. And
thank you. I didn't know how much longer you were going, so but that was about right. That was enough. So thank you for having me here, and I hope I'll have some interesting things to tell you today. My subject, as you see, will be superconducting qubits, and at least some of you know this subject here at least as well as I, because of the work of Andreas Wallraff, and maybe all of you have heard something about this subject. But I want to concentrate more on sort of future prospects of this subject. First of all, I would say that it's had a tremendous run-up in the last 12 years or so, last dozen years. And I'll review that first very, very briefly to say that we have in this subject something that's pretty unusual in basic physics, which is a kind of Moore's law, a real exponential improvement of a basic parameter, and I'll describe what that is. But I will use that to lead into the next subject of, well, these devices have improved so much, what are we going to use them for? And we're really poised for that next move into more complex devices. And I come from the perspective of someone who thinks that the really exciting thing, I mean, there are many exciting things we're going to do with qubits and with quantum information processing, but the really exciting thing is to make a big computer. That's not as I say, it's not the only thing you can think of. You can think of new ways of, enhanced communication and enhanced privacy, but I really want to factor big numbers. So I want to look forward to that day, which is still quite far in the future, and just talk about what the basic advances in device physics over the last dozen years have gotten us to. And I will tell you an idea of how it will be used, and it will very much be centered on ideas of error correction, that we have good qubits now using these superconducting devices, but in a sense not good enough, so that error correction will be very much at the heart of what goes on in reliable quantum computing. And I'll tell you how we use redundancy at quite a massive scale to turn these quite good qubits, or the prospect is to turn good laboratory qubits into perfect computing devices, perfectly reliable computing devices. There is a specific form of error correction that I'll review, which is called the surface code. And this is very topical now in physics because it actually has close relationships to other subjects of topologically ordered states of matter and things like that. And I hope I'll get to a little bit of that. And I'll put these things together and talk about a sort of picture of what this computer will look like. Now, it will still be a pretty sketchy picture, but I think we've arrived at the point where we can really draw that picture and at least discuss it rationally. and talk about how reasonable it is. So in short, we have a kind of roadmap for what this large quantum computer will look like. Now, at the end of the talk, I'll talk about how we can immediately sort of jump over the roadmap and hopefully find better ways of doing it than the sort of canonical way that we've come up with in the last few years. And that will involve two ideas that I'll briefly discuss. New schemes for error correction that improve upon the surface code, and new methods of measuring multiple qubits simultaneously that hopefully will also further improve the capability or the possibilities for doing quantum computing. So, and here's, a little saying from Feynman, who was quite instrumental in sort of starting the subject of quantum computing. And as you see already in 1985, he was featuring error correction as a crucial sort of piece of the story of doing quantum computing. So let me take you just a few highlights of what's happened in these last dozen years, just to sort of set your mind. I'm going to pass over the sort of device physics fairly fast, although it deserves a long discussion of its own. So this was a very important paper 10 years ago, in which a device was made, and it's not a very special device. I mean, it's not extremely small, it's not nanoscale, it's not made out of exotic materials, it's actually evaporated aluminum, it's just aluminum, a few layers of aluminum grown on a passive substrate. It has something called a box, and it has some small features, the place where this box meets the rest of the sample, and that's the Josephson junction. And then you see up here a moderately complicated schematic from the point of view of electrical engineering of what this circuit is. And so, this is electrical engineering, basically. There are capacitors and there are transformers, and these X's are the Josephson junctions, which are understood to be, certain kinds of nonlinear inductors, and there are AC sources and amplifiers and current biases. So a whole pile of basically, you might think, classical concepts for what this circuit is. And nevertheless, because of the basically quantum properties of the inner parts of this circuit, of the Josephson tunneling parts of the circuit, it manages to embody a quantum mechanical two-level system, precisely analogous to the two-level system, say, of an electron spin pointed up or down. And from the experiments on this device, they are able to know very precisely the energy splitting or the frequency splitting between the two energy levels, 16.4095 gigahertz. And they're able to do experiments which really confirm, this group at the CEA in Saclay were able to confirm that it indeed exhibited quantum mechanical interference behavior in the form of so-called Ramsey interference fringes. So basically it's a method of producing a superposition of the two states, of the up and down state or 0 and 1 state, and confirming that, that the phase of that superposition evolves in a predictable way as a function of time. Now, in some sense, this was a great achievement. It was, in some sense, an unexpected achievement that something so macroscopic, here's the 1 micron scale bar, so something so macroscopic could nevertheless behave so quantum mechanically. And in fact, there's many years of work preceding this that, indicate, let me jump to the next one. In a sense, this began all about 20 years earlier with work of, one of the authors being the same, but this is a paper from 1985 where a similar metal structure, superconducting metal structure with Josephson junctions, modeled by a somewhat simpler electric circuit, also showed some quantum mechanical behavior, in particular energy level quantization. This diagram shows a little bit more of the picture that this electric circuit is composed of energy storage devices, and to the extent that you can ignore the dissipative parts of the circuit, the resistors in the circuit, you can describe the dynamics of the circuit as the dynamics of a fictitious particle moving in a particular non-harmonic potential. And this was their sketch of what they thought the potential energy ought to be as realized by this circuit. And so even though, again, this was a macroscopic object, nevertheless, well, basically because of the features, the fact that it was superconducting, it was nevertheless able to see quantum mechanical behavior, the real existence of these lowest lying discrete energy levels in this potential structure. And this shows the main data of this paper, where there's some spectra, some peaks indicating a resonance, a resonant condition set up, or energy level transitions made possible by the changing of the shape of this potential. Now, for years and years, this subject was such that you could see some quantum mechanical behavior, but it was nothing near as clean as you would see in, say, the atomic levels of an isolated atom. And it was rather debated whether even the interpretation of these peaks were correct. So this subject was gestating for a long time before we were thinking about qubits or the possible applications of these things. So it was impressive, or a surprise indeed, that we were able to go from that to systems which, by changes of design, and in fact the main change of design was to make this circuit more complex, have more circuit elements, designed in such a way as to avoid certain sources of noise, basically, so as to achieve a tremendously improved manifestation of quantum behavior. Now, this data still fell far short of what you would expect for an ideal two-level system. This fringe visibility, so-called, the depth of the interference fringes was only about 10% in this experiment, and the so-called coherence time, which I'll focus on in a few minutes, was impressive, but decayed after a few hundred nanoseconds. So while we were certainly we're talking about this as a qubit, even in 2002, but we recognized it was still a rather, kind of poor performance qubit. It exhibited a lot of decoherence in the course of its operation. I might say that there was one important milestone in between, and this was, in a sense, this paper was the one that caused the greatest sensation because it was so unexpected a couple of years preceding that, in 1999. This, again, using sort of the same electrical structure, Nakamura and coworkers were able to set up by a different means, a way of making superpositions of a ground and excited state of these superconducting devices. His fringe, the interference structures that he was able to see that indicated the presence of a quantum mechanical superposition were exactly these. So they were, in fact, very feeble signs of coherence at this point. But the fact that people could see coherence at all was a great surprise in the year 1999 anyway. So it was in fact this paper that kicked off a lot of activity that led, for example, to this observation. And this paper did exhibit a big jump in the amount of coherence, the degree of quantum coherence that was seen in this kind of electrical structure. Now, this has been a big enterprise involving many, many labs around the world. And so another entry in this story, I just want to say one comment. Well, I'll leave this for a moment because I wanted to jump to this. So in my sort of timeline, a few years later, there were experiments by someone whom you know here and others at Yale University. And this was another metal structure with a couple of Josephson junctions, another, electrical circuit. What was new about this structure was that it was coupled together with a long one-dimensional structure, which is just a one-dimensional transmission line for radiation. and the frequency of the radiation being roughly comparable to the transition frequency of the qubit. And in fact, this structure is a resonator because it has it's sort of well, weakly coupled at both ends. So you should think of it as a place where radiation is trapped. Microwave frequency radiation is trapped. It served various functions. In the very first experiments, it was seen to be a good filter for noise, but it was quickly understood that it also provided a handy means of controlling the qubit and also of coupling it to other qubits. But the thing I feature here that was already present in the very first data was a very nice increase, basically all the way up to 100% of this fringe visibility. So this subject has been characterized by time after time improvements on the basic theme. That is, the basic theme is an electric circuit made of Josephson junction elements and other electrical circuit elements, leading to increases in the basic parameters of this. This, again, has a coherence time of hundreds of nanoseconds. So in that respect, this experiment didn't greatly advance on the Saclay one. But the overall trend has been towards ever increasing coherence and perfection of these objects as qubits. Let me jump back to this for a moment just to say what was going on in theory, or what kind of theory accompanied this work, and this was the kind of thing that I was involved with in these years, was that we could understand a connection, or we developed a very systematic connection between ana-electric circuit description. That is, if you looked at these objects as electrical devices and accounted for where are the capacitances and where are the inductances and where are the Josephson junction elements, we developed a formalism that would take us direct from that to a description of a quantum mechanical system, in this case, an effective two-dimensional potential, and then the quantum mechanics became, in this specific example, the quantum mechanics of a double well system, and the qubit was one which involved states localized to this left well and localized to the right well, and then tunneling in between them, or superposition of left and right would be the coherence in these examples. So there was a toolkit, both theoretically, but really more importantly experimentally, for further exploring variance on this basic structure. And you might say, from a theory point of view, crafting many, many different potential energy landscapes in which to create a quantum system. So the result of all this, I want to summarize this way. So now, I dispense with telling you all about the tremendous further physics discoveries that took place in further years, but now I'm just stepping back and looking at this almost as an engineer and talking about it. So here's the first observation of any coherence in these Josephson devices in 1999. The coherence time, that's what's plotted here, the time over which a coherent superposition of the upper and lower states are preserved is, it decays over a certain characteristic time, and that's what I've plotted here. So it went from that, and then the next experiment I showed you was up here at a few hundred nanoseconds, and then many, many further experiments which saw, an impressive further gain by orders of magnitude of the coherence time. So now, I use the phrase Moore's law. I thought I'd just say a few words about that. Moore's law, to announce a Moore's law is to announce an exponential improvement of some important physical parameter. Like in electrical circuits, it's the number of transistors that you can fit on a chip or something like that. And Moore's law was famous because for many decades that figure of merit for chips did in fact increase exponentially. And so announcing Moore's law involves nothing further than plotting some data on a logarithmic graph paper and seeing that it sort of follows a straight line. So that's all I'm saying here. Moore's law is not a deep law of science. I mean, it's discussed kind of as a law of sociology, you know, that because, of course, the scientist, you know, this was Will Oliver at Lincoln Labs, the scientist who obtained this data in the year 2010, you know, now more than microsecond coherence time in some new form of superconducting flux qubit. He didn't feel that he was just sort of part of some, you know, adding a dot to some bunch of points on a curve. He felt like he was discovering some new science. But that's actually another aspect of Moore's laws, is that they typically consist of many individual scientific breakthroughs at some level, or at least great innovations, the sum total of which amounts to some more or less regular improvement. So it's more a law of what happens when it is possible to improve something dramatically. That there's some dynamics to it that, in fact, it then it doesn't step all the way up to its maximum value. It evolves through a series of, you know, discoveries up to some high value. Now, the rest of my talk will be concerned more or less with this red dashed line, because you can say, well, where is this going? Now, you know, I could show you data from, say, this data or this data, and you would see beautiful, beautiful fringes that would just went on and on and on and on, and you know, would be almost indistinguishable from the best, you know, magnetic resonance data or fringes that you would see in some atomic physics experiment. Not quite, but getting very close to that. And you'd say, well, what's the point? You know, why do we want such a thing? And now part of the answer is, you know, you just want to see how far can this go? You know, and in fact, throughout this period, throughout this decade or so, there have been, you know, theories announced and discussed that say, well, now we'll get to 1 microsecond, but then not beyond, you know, and there'll be some specific physical effect that will just stop progress on coherence at that point. But alas, those theories didn't work, and, you know, the data kept going up. And indeed, we have theories now that say, well, they're a little more conservative at this point, but they say somewhere up here, we're going to stop. And maybe I'll say a word or two about, you know, about the actual content of those theories. But you might well ask, you know, I haven't shown you the data. This is some compilation I made up to the year 2010. What's been happening recently? Are we in fact stopped? Well, no, not in fact. That in the last year or two, well, actually in the last less than a year, there's been a whole flurry of new results, which has, as you see, I had to put more decades on my graph paper. I could barely fit it on this slide. So another more than factor of 10 increase in coherence. And so in fact, there are serious theory discussions that say that now hundreds of microseconds will come to a stop, and you hear discussions about quasi-particle effects in superconductors and, you know, other interesting phenomena, and we'll see whether that's true or not. I think that one goal of this research will be indeed to try to find the absolute limit, you know, really to find devices that take you as far up this curve as possible. I might mention that these specific reported coherence times, you see this T sub 2 is the usual magnetic resonance terminology for coherence times. These various reports are actually in a new type of structure. I showed you these planar, you know, planes of metal, thin films of metal evaporated on surfaces. In fact, these new data are all created in a somewhat different way. Sorry for the sort of psychedelic picture, but this is from some modeling software that actually these are all formed by making qubits, but then putting them not in a sheet, in a plane, but actually encasing them in a metal coffin, basically, of various possible aspect ratios. But here's, well, it's really more like a little jewel box. Here's the left half of the box, and here's the right half of the box, and you sort of sandwich it between a qubit. And I won't explain in detail why this is a good idea. It's actually a way of making a very clean microwave resonator completely surrounding the qubit, and the interaction of this one very, very clean, high quality factor resonant mode with the qubit is an excellent combination for various reasons for achieving high coherence. So at the moment, the highest coherence is being explored in these systems. But there's another point of view that says, well, getting back to the question, why do we bother? You know, why are we bothering to try to march up this curve? Is to say there's actually a very specific region. It's not exactly a very sharp line, but there's a point at which these qubits have qualitatively new capabilities, basically. And so what I indicate here is that at about this point, you know, plus or minus an order of magnitude, frankly, we reach a threshold. So the noisiness of this qubit, the decoherence of this qubit, becomes sufficiently small that, at least according to theory, it becomes possible to error correct these qubits. So the noise rate becomes sufficiently small that it becomes possible to improve their behavior by error correction. And below this threshold, these are too noisy. They're too noisy to attempt error correction on. But at about this point or higher, they should be capable of useful error correction. So I want to go through a little bit about what that means and what that implies for the further development of these qubits. Now, so far I've only been talking about the property of one individual qubit in isolation. Now, of course, one qubit doesn't make a computer, so one has to look at something more. And in fact, of course, all throughout this history, people have been looking at 2-qubit experiments, but well, in the early days, they were quite noisy. But at about the time, you know, this threshold was crossed, this is another important paper in this development. This illustrates a few things. Again, a different combination from this same group at Yale University. So this is an example of a 2-qubit experiment. Now, what's seen here in this smallish picture of this device is, again, this one-dimensional, effectively one-dimensional. The meanders don't matter, actually, for the functioning of this. It's a resonator, a one-dimensional transmission line resonator, which enables the coupling between 2 qubits, and they cannot be seen here, but there's one qubit at this junction point, at the left end of the resonator, and there's a second qubit at this junction point at the right end of this resonator. And so one can perform 2-qubit logic gates with this, and 2-qubit logic gates were indeed performed on this device, and in fact a whole circuit full of gates, of logic gates, were applied to perform something called the Grover algorithm. Now, I don't care very much about Grover algorithms or things you can do just with 2 qubits, but the important thing is that the so-called fidelity of the gate, so the closeness of the actual performed logic gate compared with the ideal, was something in excess of 90%. And so it was actually getting pretty close to you know, the actual desired ideal gate. And that more or less is what distinguishes you know, what was going on down here from what's up here. That is that once you're up in this region, you can expect fidelities way in excess of 90%. Now, I'll come to a little later, you know, what level of fidelity do you actually need? And that depends a lot on the performance of error correction code. So I will come to that. But turns out 90% is not enough. But once you get to this threshold, then it becomes possible to get, if you do everything else right, to have fidelities more like 99 or so %. And that's actually about the interesting level, the region where the sort of error correction techniques really come into play. So let me tell you a little bit about that. But to get into that, I want to talk about where one can go. There are many directions one can go. Once you've gone to 2 qubits, you obviously want to do more. This is a picture of an experiment, not necessarily the prettiest picture, but it's one that was done by former colleagues of mine at IBM, and this happens to be a 3-qubit experiment. Actually, what's more significant from my point of view is it's 3 qubits. Here they are. And there are actually 2 different resonators in this structure, so each supporting its own resonant mode. And what it means is that there's independently a coupler, or a bus, if you will, that permits 2-qubit gates between Q1 and Q3, and also between Q1 and Q2. Now, the motivation of doing this experiment, of course, most directly was to explore whether you could really do that, whether you could really selectively do particular pairs of 2-qubit gates, or 2-qubit gates between specific pairs of devices. But what excited me about this device, or what I'm really interested in concerning this device, is where it could lead to next. And I want to show you a picture of, now this is sort of an architectural concept, and this is a picture of where I believe this can go. And in fact, what structure one could build out of the component parts that would really do something powerful. And so here it is. This is a kind of tissue or a fabric of qubits and resonators. So let me point out the relevant picture. So in my little schematic, the green dots are qubits. So they aren't actually green dots, but they're nevertheless, because, well, I wanted to emphasize that these could be many different types of qubits in principle, but it's certainly tied to this superconducting proposal. So imagine superconducting qubits at all these points, and then these bars are envisioned as these buses. In other words, these resonators which permit coupling between different qubits. And so the idea of these buses, each of these buses has 4 qubits coupled to it, 2 at the ends and 2 somewhere along the middle. And this bus can mediate a coupling from any of these 4 qubits to any of these other 4 qubits. And then this basic motif is repeated periodically to make a kind of a regular square lattice, a skew square lattice. It should be mentioned that each qubit in this layout is equivalent, and each one is coupled to 2 different resonators, just like in the IBM picture, to the end of one and to someplace on the middle of another one. So now, why is this an interesting structure? Why would you want to make just a regular, repetitive structure in order to make a quantum computer? Because in fact, the claim is that this, or just a vastly scaled up version of this, but repetitive version of this, can make a quantum computer, can make actually a very well-functioning quantum computer. Now that's pretty much unlike, if I showed you a picture of a regular microprocessor, in this computer, it doesn't look at all like a regular layout. I mean, there's a rather irregular, set of wiring that couples transistors to each other. But this will in fact just be kind of a substrate or a fabric on which the quantum computing is built. So let me describe, the functionality of that substrate. So this is just to get back. So now I'm about to tell you about the so-called surface code, which this embodies. So the surface code has a history that goes back quite a while to the early days of quantum information theory, and it was published in this rather obscure paper. It's rather hard to find this paper even, although there were follow-ups that are much better known. So this is Kitaev, and he proposed something called the Toric code, or it's also referred to as the surface code. So it's stated as a quantum, really spin lattice Hamiltonian. So it's stated as a quantum sort of solid state physics object. And it's envisioned as something, so there's a regular square lattice of qubits. They happen to all be centered on the centers of these edges, not at the vertices. And he asked he introduced something called stabilizers. I mean, well, it had been introduced already in the theory of error correction. But they are intended to be quantum operators, and you can think of them as spin operators or Pauli spin operators. But they're ones which are products of spin operators, in fact, products of 4 spin operators. So products of sigma x, of the Pauli sigma x operator on 4 neighboring qubits forms a so-called star. So that's one type of operator that he introduces. And then there are so-called plaquette operators, which are products of Pauli sigma z operators around a square of 4 qubits. So what he observed is that those operators, if you summed over those operators over the entire lattice, periodically over a whole lattice, it would have several properties which are all equivalent but could be said in rather different ways. One is that the ground state of that, viewed as a Hamiltonian, was highly entangled and with no local order, and the no local ordering actually went along with the property that the states were also very robust to fluctuations of the Hamiltonian. So if you added local fields, for example, to that Hamiltonian, the state would be hardly disturbed. Now, this was also understood in the language, in an informatic language, that it's an example of an error correction code, and it says that if the state of the system, if the state of these, I'll call them now qubits, is in an eigenstate, a low-lying eigenstate of each of these operators separately, so it can be at the same time an eigenstate of these x's and also an eigenstate of these products of z's, that state is one that is strongly error-corrected, in the sense that if some qubit is flipped, then a measurement of these operators, a measurement of these 4-qubit operators, will detect the occurrence of that flip, and then that flipping can be repaired locally. So there are 2 very different points of view about this model. It actually didn't get a lot of attention for quantum computing for a while, for not very deep reasons. It turns out as a code, it doesn't have high rate. Now, I won't define what rate is, but it's something that is very relevant if you use this as a code for doing communications. Now, that indeed was not the relevant point. We're not going to use this code for doing communications, reliable communications. We're going to use it for doing reliable data processing. And so the original thoughts about this were a little bit misplaced. So it didn't develop very fast. And in the standard textbooks at that time, it wasn't even mentioned, unfortunately. But so let me tell you what I'm now going to make contact between this Kitaev model and concretely what goes on with these superconducting qubits. So you have a square array of superconducting qubits. What do you do with them that sort of makes the Kitaev model, that sort of creates the Kitaev state, this error-corrected state? So I'll use an intermediate level of abstraction. Here's an array of qubits, and I'm going to imagine they are actually physical qubits. I think I will comment a little later on how this really concretely connects to this skew-square lattice. But you just imagine these are qubits that you can physically couple along nearest neighbor links. So if you translate Kitaev's prescription into an operational language, then you do the following steps. You take a sublattice, and I want to describe this just so you can understand, if you understand anything about these sort of elementary quantum circuits, that this is really a very concrete and pretty simple sequence of steps that you do that accomplishes a very powerful error correction procedure on this lattice. So the first step is you take 1 out of 4 of each of these lattices. So you take a sublattice, a superlattice of this square lattice, and each of these qubits you initialize to their ground state, or to the 0 state. So far we'll describe all these other qubits will get involved, and the color coding will help in a minute. So that sort of initializes the work that you're going to do to implement this as an error correction code. The first step after that is to do what's called a controlled knot. I think probably you know what that is. Well, it's a logic operation in which the bit or qubit, I mean, it's well defined either as a quantum logic gate or as a classical logic gate. You flip this bit if this bit is a 1. That's what this symbol means, this double-headed symbol means. And otherwise, you do not flip this bit. So that's the sense in which it is a controlled negation of the qubit. So you do this specific array of controlled knots all throughout the lattice, or however big a size of lattice you're going to do. I'll call that the controlled knot left. You know, controlled knot from going from right to left, and then followed by controlled knot down. So just a different superlattice of controlled knots, then controlled knot right, then controlled knot up. And then we do something different. We actually measure these qubits. We measure the qubits that had been initialized to 0. And the idea is that if they're still 0, that's a sign that no errors, no decoherence, basically, has occurred on the qubits. And if some of them are measured to be 1, it's a sign that some decoherence, some errors have occurred, and they will form the basis of how you fix the state of the qubits. And you'll fix them, it turns out, by also simple local operations. Now, that's only half the work. But the rest of the work is a strict dual of what I've just shown you. So you take another superlattice of these qubits and you initialize them to what I call plus here, which is an equal superposition of the upper and lower state, of the 0 and 1 state. And then you do a shifted version of the controlled knot arrays, now involving this qubit that I've initialized differently. So C naught right, C naught down, C naught left, C naught up. And then finally a measurement of those, but now also a measurement in a different basis. And you have to measure whether it's in the state 0 plus 1 or 0 minus 1. And that tells you about errors in a different basis, so to speak. So, and that's it. And then you just repeat that pattern that I've just gone through over and over and over and over again. So the running of, that establishes the fabric of quantum computation. And in a sense, those are the only gates you ever run in this computer that I'm going to describe. So it's a very monotonous thing. You have to do something with it at a higher level of, higher structural level in order to actually make it run useful computations. But let me say a few things about what that gains you. I come back to this. So that does mean, by the way, that each qubit has to be capable, or many of the qubits in this lattice has to be capable of being measured. And maybe I'll return to this theme later. So I have various structures here that I haven't described. I mean, this is all very schematic, but some other structures that are designed to read out the state of many of these qubits. And whenever you see a yellow square in this picture, it's a place where classical signals, microwave signals, have to come in and out of this chip. That's perhaps the scariest aspect of this whole picture, that you have a very dense collection of signals that have to be entering and leaving this chip in order to make all of this stuff happen, make all these controlled knots happen and measurements happen. Okay, now, be that as it may, let me just summarize what I just, or to make the contact between this U-square structure and the thing I've been talking about abstractly. It's just to say that if I deform the cavities, so these green things now are denoting the cavities, which I've sort of stretched in order that they contact the qubits that they do. And it turns out this is the geometry, and this is indeed a geometry where you can accomplish all the necessary near-neighbor qubit-qubit interactions. So you're invited to parse that, by looking at the podcast if you're really interested. Now, just to say, I'm going to summarize a huge amount of research in one slide, that this is a fabric now, and I've gone to a somewhat further demagnification. I imagine a patch. This is just PowerPoint, so I can make hundreds of qubits in PowerPoint anyway. So I have a whole lattice full of qubits, and the way this is sort of a developing story, but the way we understand algorithms to be done is in a kind of higher level topological fashion. In short, what you do is you make holes in this lattice, So holes just means regions where you don't do all of these error correction operations. Now that seems paradoxical that that would be a useful thing to do, to stop error correcting in a certain region. But it turns out the presence of a hole will actually, or the state of the qubits around the hole, in fact, encode quantum information and in fact make an effective qubit, a really data-carrying qubit. And then the fundamental operations of doing quantum algorithms involve moving the hole around. And in this picture is a description of exactly what do you do to move a hole. You actually lengthen it first and then shorten its tail end. But then the pictures of what algorithms actually look like are these weird beasts. And these are actually space-time diagrams of taking this, which is a snapshot of what happens on one plane, sort of at one time step or at over a small sequence of time steps, and stretching it out. You know, this is now going to be, let us say, hundreds of time steps of operations. But over that time, you create holes and you sort of wind them around other holes and then join them back together again, so you get these kind of loops. And this sequence of things actually does a specific algorithmic task. You know, it's a specific module that's used in quantum computation. These have been, as I say, extensively simulated. Here's just one piece of this literature that's particularly informative, this Fowler et al. Paper in 2009. It's a whole, you know, mathematics of its own, I would say. It's not really physics, and I'm not sure if it's computer science either. I'm not sure what it is, but anyway, but the thing I want to feature here is that among all the studies of this work are extensive simulations of exactly how reliable the qubits need to be in order for this whole procedure to work. In order for the error correction procedure not to get overwhelmed by too many errors. And the threshold of noise rate per gate operation is about this number, about something close to 1%. So that means that if, turning that around, 1 minus that, if the fidelity of the gate operations is something like 99% or in excess, somewhat in excess of 99%, then this whole procedure closes. And it becomes possible to create a quantum computer in PowerPoint. So that's not quite the same as creating it in the laboratory, but at least it gives sort of a design target. So let me wrap up. I have to say that when I always saw these pictures, I don't know if you see these anymore, but my screen used to get filled with these kind of things. This is called this is the Pipes Screensaver. So, and you know, the evolution of these lines, these tubes, look somewhat like what this screen used to look like. I don't have a sort of live version of it, though. So, let me jump, though, to, I want to take you into another paper. So among this literature, here's a paper from optically controlled quantum dots. Now, this is just to illustrate a few different things. One is that this whole concept, this sort of surface code concept, or these architectural concepts are not confined to just these superconducting qubits. And in fact, this is a paper, this is from the Yamamoto group. Some of you know that, the Stanford group that works on optically controlled quantum dots. So this is a picture. It's from a physical review paper, but it's also, you might say, a kind of science fiction or, you know, future projection. So they ask you to imagine an array of quantum dots, again, square array. I mean, it's square for exactly the reasons I've been telling you. And they have in mind some control. You know, these quantum dots are in some Bragg mirror cavities. So again, cavity coupled. And the big difference is that instead of electrical pulses coming in and out to control the gate operations, they imagine, as they say, laser light, you know, being shown into this thing in the appropriate pulsed fashion. I do not think, as I say, this is not my preferred embodiment because these qubits have really not proven themselves. They do not have the kind of fidelity performance that I've been discussing. But nevertheless, you can, you know, if you postulate that they do get good enough, that they do, their coherence does improve and their fidelity does improve, you can imagine what a computer will be like. And what I like about this paper is Jones et al. Went all the way to imagining how big does this lattice have to be to do a really big factoring algorithm. So really shake up the cryptography world. They're going to factor a 1,000-bit number with this puny little array of quantum dots, but with all these holes and pipes and all that kind of stuff. And what you find, or their study indicates that they call virtual qubits, but to them virtual qubit is just one of these self-assembled quantum dots. They need 500 million, 400 million quantum dots. They hope that the error rate is 0.1% in order for all of this to work. The reliability of the processor itself is one logical operation part in 10 to the 20. So that's just to indicate how reliable this is supposed to be. This redundancy, this is a huge amount of redundancy that's being built in, but what you gain is that you'll get processing power or processing accuracy that rivals, a Pentium, that you basically, one time in 10 to the 20 operations a mistake is made, so basically never. So that's what I wanted to feature, and they optimistically say that this could all fit on a chip, rather modest-sized chip, because these quantum dots are only a micron apart, and the execution of the algorithm would only take 2 days. So there you go. But I think well, in my opinion, the quantum dots fall short, at least for the time being, the optically controlled quantum dots especially. But the future vision is more or less right, as far as I'm concerned. That is, that if I say all these words for the superconducting qubits, I think it's plausible. So let me conclude by just saying a few things about, well, I see that I've really run out of time, so I'll have to say this very quickly. So this Jones et al. Paper came out, and immediately you said, oh, we can do much better than that. And of course, that's natural. That's what's good about roadmaps, is that you can immediately look at them and say, oh, I can beat that. I can get way ahead of them. If they stay on that roadmap, I can make a shortcut and get way ahead of them. So I'll just very briefly state what those things are. So remember, Kitaev had these 4-body operators. And why 4-body? Well, there was actually long literature about that, but the short answer is it wasn't necessary, but it took until this year to realize that basically the same thing can be done and the same threshold can be achieved with just a different pattern of qubits, but 3-body operators. So we should redesign everything to adapt to this so-called subsystem toric code. So that's already a big improvement. The other thing that I just want to comment, this is just to advertise that I've been doing some recent work on this myself. All of these things prescribe certain measurements to be done. They can be thought of as things where you do a sequence of gates and then make some measurement. But you can ask the question, why can't I measure the operator prescribed by this directly, z, z, z? That actually just means the parity, that is, of these 3 qubits, that is, whether they're even or odd, whether the combination is even or odd. And I can just advertise that we have ideas for how you could do really getting away from the gate paradigm of quantum information processing, that just using direct microwave scattering concepts, so you can build a structure that will directly extract, do the right kind of non-demolition measurement and actually extract the 3-qubit parity. But in the interest of time, to get to the question period, I will skip over that. And just come back to this for a moment and say that while this has perhaps something of a kind of flavor of science fiction, I think that if we are going to build, machines that factor 1,000-bit numbers, that we will have to have some structure like what I've described. I mean, it was something that presently looks really fantastic because we don't make physics experiments with millions of qubits. But if we're going to make computers out of them, there will have to be millions of qubits. And this is a very, very plausible, first attempt, view of what that machine will have to look like. Just to close with some amusement or current view, because in contemplating this machine, this subject began with these kind of thoughts, and there was Norman Margolis, who was a very early thinker in quantum computers, understood actually that a quantum computer could function in a way where you just, you make something, you seal it up in a black box, and you just walk away from it. You don't make sure not to touch it, and then you come back later and open it up, and there's the answer. That is, possible in principle. But in fact, we've gotten to a very different vision of a quantum computer where, in fact, it's being intruded upon constantly by signals, pulsing it, saying, do this, do that, measure this, measure that. And that, to me, it more sounds a lot like a particle detector because, particle detector is something that has, deep inside it, actually on a line rather than in a plane, some, kind of pretty subtle quantum mechanical stuff going on. But under constant, massaging and measurement, so lots of cables coming in and out. So I think at some scale, maybe a somewhat smaller scale than this, the quantum computer will be a gizmo that looks sort of like this. Notice I picked just a puny little old Fermilab detector and not the Atlas detector, which fills the whole building. Well, this, just to contrast also, this goes back to earlier thoughts about regular computing that my colleague Charlie Bennett discovered that there's no lower limit on how much energy consumption is needed for computing. There's a very fundamental discovery of computer science, and yet we still burn gigantic amounts of electricity, servicing our Google queries. So that's all, and I thank you for your attention.
Thanks, David. Are there any questions? Sure, there must be. Renato?
So you mentioned the translational invariant structure of these lattices. Is there really a technological advantage for these type of qubits of this translational invariance? Or if someone invented now a code which would not have a translational invariant structure, would that be harder to implement? Because in principle one can manufacture any circuit.
Well, it depends. Yeah, it depends on what breaking of translational invariance you have in mind. Because I do think that sort of random logic, long distance connections point to point, is awkward to envision quantum mechanically. That this sort of locality of quantum physics is a much more natural thing to imagine. Now, if you want to imagine something that still only has fairly short distance interactions, but maybe there's some interesting modulation or even fractal character of the overall structure, I wouldn't exclude that. And in fact, I mean, maybe you know, or there is indeed work very currently on error correction codes which really build new kinds of fractal structures and announce them as interesting new kinds of error correction codes. I don't know if they will rise to the level of being sort of technologically interesting.
Any other questions? John?
So usually you start with devices which operate on an energy scale. Then you build a structure out of it which has an emergent new energy scale and so on. So that is sort of the generic principle of getting protected. Now these devices, what will be the energy scale? Will it be Kelvin, nano-Kelvin, or what will protect these devices in the end?
Well, there are sort of two answers to that. It depends on whether you take Kitaev's original view that what we're talking about, say, in these structures is the implementation of a Hamiltonian on this lattice, a real effective Hamiltonian, or whether it's a prescription for doing a sequence of measurements. If you take the Hamiltonian view, then well, I have a little trouble answering that because these qubits are not designed so that they really implement these four-body interactions in any direct sense. Naturally, for other reasons having to do with the devices themselves, this works at tens of millikelvin, and you don't need to go below that. I mean, they should. All the ideas work if you work at those kind of temperatures. The dilution refrigerator temperatures where the individual qubits work well. The funny thing, though, is that when you think in terms of this as a prescription for measurements, you sort of take energy scales out of the problem. You know, what energy scale do you associate with a quantum measurement? You know, it's a projection operator. You can talk about the time it takes to do the measurement and turn that into an energy, h bar over the time or something like that. But it's not clear that that's the energy or whether that sets an effective temperature of any interest. And it's basically because it's a highly non-equilibrium setting. You know, you're not working near the thermal equilibrium of this structure. You're constantly far, far out of equilibrium. And that's the point, in fact, of making devices with such long relaxation times is that it's okay for them to be out of equilibrium for almost forever. So those are a few of my thoughts about that question.
Are there any other questions? Yeah, there's one.
Can you elaborate a bit more on this idea about computing doesn't need energy?
Oh, well, I love mentioning it because I think it's you know, one of the most fundamental discoveries about computing. It arose, Charles Bennett is a longtime colleague of mine at IBM. The way I understand it is it goes back to actually von Neumann, who considered, you know, what are the fundamental sources of dissipation in computation. And he thought that there were, in fact, you know, whenever you do an OR logic gate or an AND logic gate, that there would be a minimum dissipation. And I mean, he announced a value for that, which would be K sub Boltzmann T times the natural logarithm of 2. So that's his formula. Landauer further traced it down and saw that it really was not due to the logic operation itself, but it was due to the erasure of the bit, of the one of the two bits at the end of the logic operation. So, it's now sometimes called Landauer's principle, that whenever bits are, so to speak, thrown away, that you have that amount of energy lost to the environment. But then it was Bennett who found that in 1972, he found a scheme for computation that was both efficient and never erased bits. That all bits were always reset to zero in a controlled fashion rather than in an uncontrolled fashion. He showed that that was possible within a physical model of computation, at first within a Turing machine model, and then later with other colleagues like Twolevel within a gate model. So that's a very brief summary of the history of what's called reversible computation. But, you know, of course, it's sort of like, I like to say that Bennett's discovery is basically like expressing Galileo's discoveries as saying that we have reversible transportation. You know, that we can go from one place to another without expenditure of energy. But of course we do. We spend a lot of energy getting from place to place because we're very impatient. We want things to happen fast. And for that you need energy, apparently.
What is the aim for computations in this technical enterprise? I mean, what do you finally want to compute, not factor numbers, or do you want to...
Well, I have a kind of... I kind of have an idealistic answer to that question, you know, why do we do this? We learned a few years ago a very surprising fact, or, well, evident fact, I guess I can mention a few loopholes, which is that the class of computations that can be done in this quantum model is actually larger as a set than the set of computations that can be tractably done in a model coming from classical physics. As I say, we can't prove this. I mean, there are things about, you know, the collapse of complexity classes is possible but not expected. So there is a class of problems that should be available to us, but we just have to build the right machine and then it can be done. And so I always say, you know, what we're striving for is to build the BQP machine. Sorry, BQP, bounded error quantum polynomial. That's the name of this complexity class that nature permits us to do that, and so we should do it. And then we'll find all sorts of things to compute, like we did when we started building digital computers. Now, there's a sleazy answer to that question, which is that the customers who are paying for this, especially in the United States, really want to factor numbers. And they're paying a lot of money for people to try doing it. So, so the two motivations mesh very nicely. I've left the United States, notice.
Well, are there any other questions? Then I suggest we thank David again for his